Hello everyone. I hope that you are doing fine and you are safe with this current situation. So today I'm gonna start the chapter 4 as I explained in the past weeks, the chapter 1, 2, and 3 in a regular classroom. So today I'm gonna start my first e-learning lecture as I hope that the struggled situation will be ended soon and we return soon to our classroom. So as you remembered in our chapter 3, we took the autonomic nervous system, and I have explained in this chapter the subdivisions of the autonomic nervous system and its subdivisions into parasympathetic and sympathetic divisions. Today, I'm gonna continue the ideas related to the autonomic nervous system by explaining what are the cholinergic agonists. To start, just a kind remember of what is the cholinergic neuron. As you remember, I have mentioned in the chapter 3 the type of neurotransmitters synthesized by the neuron of the autonomic nervous system. And I said that usually there are two main neurotransmitters. One of them is the acetylcholine, and the other one is the norepinephrine. As you know that the neuron that synthesized the acetylcholine is known to be a cholinergic neuron. If you look at this scheme, you're gonna find that the cholinergic neurons are found in the preganglionic fibers of the sympathetic division that innervate the adrenal gland. They are also found in the preganglionic fibers of the sympathetic and the parasympathetic division, as well the postganglionic fibers of the parasympathetic division uses also the acetylcholine. And regardless the autonomic nervous system, the somatic nervous system works also by using the acetylcholine as a neurotransmitter. And all the neurons that use the acetylcholine as a neurotransmitter are identified to be known a cholinergic neuron. Now, how the neurotransmission happen at the cholinergic neuron? As you know, the cholinergic neuron is a long cell. As a regular neuron, it has a membrane, it has the cytoplasm and organelles present in that cytoplasm. At the membrane of the cholinergic neuron, you will be finding a transporter. This transporter is specifically a co-transporter. It means that it transports two elements. One of them is choline and the second one is the sodium. The choline is an essential nutrient that it is naturally present in food and is a source of methyl groups needed for many steps in metabolism. So when it is given or supplemented in food, it enters the neuron by co-transportation with the sodium. Once it becomes inside the neuron, the choline will be acetylated by the addition of the acetyl-CoA to form the acetylcholine. And this reaction is catalyzed by the enzyme called acetylcholinesterase. The formed acetylcholine will be enclosed within vesicles, and these vesicles protect the acetylcholine from being degraded. This vesicle needs to be transmitted or transported close to the presynaptic membrane in order to help the neurotransmitter to be released into the synaptic cleft. This transportation of the vesicle requires an influx of calcium that it is involved in increasing the contractility of the neuron and therefore the passage of the vesicle from the inside of the neuron to the presynaptic membrane. The released neurotransmitters into the synaptic cleft put the acetylcholine in front of 3 fate. The first fate is the acetylcholine binds to its receptor present on the postsynaptic membrane, and therefore an intracellular response will be seen. The second fate is that the acetylcholine binds its receptor present on the presynaptic membrane and exerting a feedback or a returning back into the neuron. A third fate is the degradation of the acetylcholine by the acetylcholinesterase into choline and acetate. The cycle of the acetylcholine resynthesis will be repeated by the reuptake of choline by the same co-transporters as it started before. This uptake of choline can be inhibited by a drug called hemicolinium. Note that the vesicle containing the neurotransmitter can be released or can be or not released depending on the action of two different toxins. If the patient will be infected with botulinum toxin, then the release of the neurotransmitter from vesicle to the synaptic cleft will be blocked. However, the spider venom causes an increase in the ability of the neurotransmitter to be released into the synaptic cleft. Now, the acetylcholine cannot make its function without binding a cholinergic receptors. The cholinergic receptors are of two types. On the basis of their different affinities for agents that mimic the action of the acetylcholine. The first type is called nicotinic receptors, and the second one is called the muscarinic receptors. As you know, both receptors are also acetylcholine receptors. Both receptors, nicotinic and muscarinic receptors, are found in the central nervous system and in the autonomic nervous system. However, at the neuromuscular junction, I do mean in the synapse that involve the interaction between a neuron and a muscle, the acetylcholine receptor present on the muscle is of a nicotinic type. The muscarinic receptors are receptors that, of course, bind the acetylcholine. But in addition of the acetylcholine, they have also the capacity to bind another molecule called muscarine and another one that it is called nicotine. The muscarinic receptor has a high affinity to bind the muscarine, while a low affinity to bind the nicotine. There are 5 subtypes of muscarinic receptors labeled from M1 to M5. The M1, M4, and M5 are found in the central nervous system, while the M2 is mainly found at the level of heart, and the M3 is found at the level of the smooth muscle. We know that if the patient will be taking a drug that mimic the muscarinic actions, then it, of course, preferentially stimulate the muscarinic receptors on these tissues. And if it is provided at high concentration, then the drug mimicking the action of the muscarinic receptors can also bind the nicotinic receptors only once it is provided at high concentration. Now, how the muscarinic receptors acts? They act by activating a G protein. So the muscarinic receptors belong to a G protein coupled receptors. We know that the M1, M3, and M5 are stimulatory receptors, while the M2 and M4 are inhibitory receptors. So how do they exert these functions? When the acetylcholine stimulates M1 or M3 or M5, then it activates a G protein. Remember that a G protein is made up of 3 units, alpha, beta, and gamma. Once they are activated, then the beta gamma will be separated from the alpha subunit that goes and activates an enzyme called phospholipase C. This enzyme breaks the phospholipids present at the membrane of the cell into inositol phosphate and diacylglycerol. The diacylglycerol activates a kinase, protein kinase C, that it is involved in phosphorylating certain proteins, leading to a response. As well, the IP3 binds its receptor present on the endoplasmic reticulum, activating therefore the calcium channel to open. And the calcium will be then released into the cytosol, where it causes also the response that it is known as contraction. And therefore, the M1, M3, and M5 once activated causes a contraction in the membrane where they are present. That's why we confer to them a stimulatory action. Regarding M2 or M4, once they are also activated by the binding of acetylcholine, they also activate a G protein coupled receptor that are involved in causing the inhibition of the adenyl cyclase by the alpha subunit and the increase in the activation of the K plus channel by the beta and gamma subunits, causing an increase in the influx of K plus to the outside of the cell. So we conclude that the M2 receptor activation causes a loss of the positively potassium charged, leading to a decrease in the heart rate and a decrease in the neurotransmitter release from the cholinergic nerves. That's why we also confer to the M2 and M4 an inhibitory role. When the M1 receptors are activated, such as by the acetylcholine or by any other agonist, then they will be used in this case to investigate the treatment of an Alzheimer patient. The use of antagonists of M3 receptors is known to be involved in the treatment of patients having a COPD, which is known as a chronic obstructive pulmonary disease, which is known really a high infection in the trachea, in the respiratory airways.